Welcome back. So this is now the first of our three approaches to diffusion. And as I mentioned in the previous introductory vignette, my logic here is that I wanted to give you an opportunity to see diffusion from three quite diverse points of view, all of which are really useful for forging ahead in all sorts of different scientific endeavors. So the first of the three approaches comes down to a really, in some sense, very strange idea, which shows the pervasive influence of the mathematics of coin flips. You know, we already introduced this in the context of carboxysome segregation and in the context of macromolecular partitioning, where we argued that in cells as they divide, one way to at least hypothesize the nature of the dynamics of that cell division is that the proteins actually flip a coin to decide which of the two daughter cells that they go to. So now what we're going to do is we're going to find ourselves in a similar boat, but this time thinking about diffusion from the point of view of coin flips. And let me just try to give you a little bit of a sense of why that might make sense. So if you hearken back to the last vignette, you'll remember that I introduced the work of Jean Perrin, who was this French scientist that did microscopic observations of the Brownian motion of various kinds of particles. And the thing I guess I'm going to try to push here is that, you know, we have our random walker, and this is at t equals 0. And then for the moment, I'm going to think about just a one-dimensional diffusion problem. 1D diffusion. And so this walker flips a coin, and if he or she gets a heads, then moves to the right, so that's a heads. And if tails, moves to the left. And let's say that in the first time step, so this is t equals delta t, now the walker's at position h. And at the next instant, the walker flips another coin and either goes right or left based on whether or not they get a heads or a tails. And basically we accumulate a particular trajectory as a realization of a series of coin flips with the heads and tails basically illustrating whether or not the walker went left or right. If we were in the classroom right now, and I'm going to give a little bit of another one of my vignettes in which I complain about the nature of this online experience, but if we were in the classroom, what I would do at this point is it would basically stand at the center of the room, and then I would point at each of you and I'd say, you know, even or odd, with reference to whether or not you were born on an even or an odd day. And if you were born on an even day, that's a heads, and I'd move to the right. And if you were born on an odd day, that's a tails, and I'd move to the left. And I basically perform a little dance for you, and what you would find is that on average, I really didn't get anywhere. In other words, my average position would be the origin where I started. But over time, you know, because of the accumulation of fluctuations, I would actually end up getting farther and farther away from the origin in a way that goes like the square root of the number of times that I did this little experiment with your birthdays. So we're going to imagine a one-dimensional diffusion, and the way that, you know, you might think about this is that the walker starts at the origin, and you know so here's the starting point, and in the first time step gets a heads, and so moves to this point. The next time step gets a tails and moves to here. The next time step gets a tails and moves to here. The next time a heads, next time a tails, next time a tails, next time a heads, tails, tails. And so with each time step, a coin is flipped and the particle moves. That's it. That's the entirety of our model, you know, and in some ways, this is one of those moments where, you know, I can't speak for anyone else. I can only speak from my own experience. But there were so many times as I was trying and struggling, really, honestly, to learn physics, where I just thought, well, this seems so contrived, and it seems so overly simplified somehow. And what could this possibly have to do with the natural world, which I so love and enjoy looking at and trying to reason out? And yet, you know, what I understand again and again is how naive I was. In other words, it's funny, you know, my judgmental self thought that science was naive, but in fact I was the one that was naive and not appreciating somehow the power of simplicity and abstraction. So here, you know, we make this super simple picture of diffusive dynamics, and yet it leads to, you know, very interesting and compelling behavior. And, you know, that's shown here at the bottom, where, you know, this is just in anticipation of where we're headed. But what you can see on the left here is that we're looking at a bunch of different realizations down here. Each color is a particular trajectory. In other words, we choose walker number one, and we tell walker number one, do a bunch of coin flips and then plot your position as a function of time. And then we tell walker number two, you do the same thing. And so what we'll find is, each particle has its own trajectory, and that's fine. They all have their own trajectories. But if I statistically average, which is to say, I plot a histogram of where they are all find at different time steps, that's what's shown here. So time is advancing in this direction. And what we see is that they all start out at the origin. That's this delta function at the origin. But over time, this thing is a Gaussian, and it's a Gaussian that's getting broader and broader and broader over time. And another way of pointing that out is to say that if we plot the mean squared displacement, so here what we're plotting is x squared, which is equal to 2 dt, what we'll find is a linear relationship between the x squared, the mean square displacement, and time. So very powerful ideas. So what we're going to do now is we're going to try to implement all of this using mathematics. And before I do that, let me just try to give you a little bit of a sense of what the game is. So as I already noted, our random walker starts at the origin, and she flips a coin. And if she gets a heads, as shown here, she steps to the right. And if she flips a heads the second time, then she moves to the right yet again. And then on the third time step, she flips a tails and she moves to the left. That's it. Now, what we're going to do is we're going to actually think that through from a sort of more careful point of view. Instead of thinking about the specific realization, we're going to do all trajectories at once, so to speak. In other words, well, let's examine it. So walker starts at the origin. At time step number one, she flips a coin. And as a result of that coin flip, she has a 1/2 chance of going one step to the left, and she has a 1/2 chance of going one step to the right. So the probability of a left step, or said differently, the probability of being at A, P at minus A, is 1/2. The probability of being at A is 1/2. So both of those things can happen. Now, if the walker is at position minus A, and the next instant she will flip a coin again, and if she flips tails, she'll end up over here at minus 2A. If she flips a heads, she'll go back to the origin. If she was at A and flips a tails, she'll end up at the origin. If she flips a heads, she'll end up at 2A. And so those things have relative probabilities 1/4, 1/2, and 1/4. And you can actually reason this out because, and actually I might be inclined to write this middle one, this 1/2, is the same as 2/4. So the probability of being at a given position is the number of ways of arriving at that position. So what I want you to notice is that here there are two paths to the origin, this path and that path. There are two ways to get to the origin after two flips. There's only one way to get out to minus 2A. And there's only one way to get out to plus 2A. So there's both there's a statistical weight, and then there's a multiplicity aspect. In other words, how many different ways can a given thing happen? So what I propose to do here is that I propose maybe we can try to make a table, and in this table, what we're going to do is we'll figure out the relationship between number of steps. So that's my first column, and then average position, and that's my second column, and then average x squared in the third column. Let me, I don't know what happened, but let me, once again, I'm sorry about this. I do indeed have some technical difficulties. I don't know why it kicked me off, but I'm asking for your patience. This whole arrangement is not pleasant, but that's the way it goes. Okay, so what I want to do is I've started this table, and after one step, the walker can be at position minus A with probability 1/2, or at position A with probability 1/2. And so that means the average position is 0. For x squared, well, I take the position, square it, and then multiply by the probability. And so in this case, I get a squared. So after one step, the mean squared displacement is a squared. That's interesting. Let's try after 2 steps. So after 2 steps, the walker can be at minus 2a with probability 1/4. The walker can be at the origin with probability of 1/2, and the walker can be at 2a with probability of 1/4, and that gives me an average position of 0. And this is going to continue. It's equal to 0. No matter how many time steps that I've taken, the average position is 0. Okay, so I'm not going to belabor that. I'm not going to work that out any further. For the mean squared displacement, here I have minus 2a squared times the probability of being there, which is 1/4, plus 0 times 1/2, and then plus 2a squared times 1/4. And if you reason that out, what you'll see is that that gives me 2a squared. So the mean square displacement is starting already to show a little bit of a pattern. We could conjecture that after n steps, okay, after n steps, I'm conjecturing that the average position is 0, and I'm conjecturing that the mean square displacement is na squared. Okay, let's just check it out after 3 steps. After 3 steps, the walker can be at minus 3a, which I square with probability 1/8, can be at minus a with probability 3/8, can be at plus a with probability 3/8, and can be at plus 3a with probability 1/8. And that gives me, well, 3 squared is 9, so I have 2 of those, that's 18. And what am I saying? So, yeah, and then plus 6, that's 24 divided by 8, so this gives me 3a squared. So, you know, what we've confirmed is this conjecture. I shouldn't say we confirmed it. We see the pattern continues, and the confirmation will actually come in the form of a homework in which you use the binomial distribution itself to work out this the mean square displacement. So what is the conclusion? The conclusion is that average x squared for this random walker is given by na squared, and n is equal to the total time divided by the time step. So I could rewrite this as a squared over delta t times the time. And this thing is got units of length squared over time, so this is our diffusion coefficient in our little toy model. So as I said before, if you were to take up a simulation, which you will, what you'll find is shown on the right, which is plotting the mean square displacement as a function of number of time steps elapsed. And what I want you to appreciate is that, you know, we get this either out of doing a stochastic simulation and averaging over all the different realizations, or as you'll see in a homework, we also find it by the simple statistics of the binomial distribution, because we know the probability of being at all of these positions as a function of time based strictly on the ideas that come from the binomial distribution. So I think those are the main points that I wanted to hit on for this analysis. I mean, maybe what I should do is just, you know, foreshadow that the probability of getting nr steps to the right given n coin flips. So this is number of right steps. and this is the total number of steps. This thing is, as we already found in our earlier vignette about the binomial distribution, is given by this simple relationship, and I'm acknowledging the possibility that the coin flips are not honest, so this is a probability of a heads. So this is telling me that if I want to know out of a total of capital N coin flips, the probability that NR of them will be to the right or will be heads, then this is the probability distribution. And I also wanted to note that how far the particle will have moved is going to be given by the number of right steps minus the number of left steps times A. So this is the displacement. So from that I learn if I want x squared, then that's going to be nr minus nl squared a squared, but I can always acknowledge and use the constraint nr. Sorry, I kicked off again. Please bear with me. Frustrating as heck. So NL is n minus nr, and this is squared times a squared, which I see is the same as 2nr squared, 2nr minus n squared a squared, and hence average x squared is equal to average looks like I'm striking out on being able to finish this video. Well, let me try one more time. Please be patient. Sorry. So what I was saying is that this is 2nr minus capital N quantity squared. The angular brackets refer to averaging, which I can always rewrite as 4nr squared minus 4nr capital N plus n squared. This is all averaged a squared, which is 4 average nr squared a squared minus 4 average nr times n a squared plus n squared a squared. So that's basically the ingredients, the fuel that you'll need in order to complete things, because at this point all that remains is you need to use the binomial distribution to find nr squared and nr. And I remind you that this one is n times p, and average nr squared, that's for you to find out, because it's fun. And so when all the dust settles, what you're going to find is that is precisely the relationship that I already worked out myself, sort of by scratch and sniff, which is this NA squared. Okay, so with that, that's the end of the coin flips version of diffusion, with many of the details left to you for the upcoming homework.